Okay, so now in the final part of this lesson, and actually the final lesson of the year, we're going to actually find the area of the plane region, and we're going to find a way to find it exactly. No more estimates. Since we know from our previous lesson that we can apply the concept of limits and find a limit at infinity of a summation, we can actually find the exact area underneath this curve. And the formula is given to you right there, but it is not anything new. Despite the fact that it looks a little bit crazier, it is the same idea. We're still going to be looking at the following. This is still going to be the height times the width. And that's going to give us the area of any one rectangle. And we're going to add up all of the area of each rectangle. And we are going to take a look at the limit of that summation as n approaches infinity. So this is still the sum of f of x times delta x every single time. So what I have from our previous discussion up here, all that we were doing here, we're now just taking the limit of this as n approaches infinity, okay? So don't let the fact that we have a little bit more written down here scare you, okay? But with that said, I still want to highlight a couple of quick things. First off, note that right now we're talking about a and b. Well, what is a and b here? That's the interval for which we're integrating, or the area for which we're bounding our region. So a would still be here and b would be there, okay? So in this case, b minus a, we can say b minus a is equal to 1. And that makes sense, because if b minus a is equal to 1, n represents the number of rectangles that we have. N is the number of rectangles. If n is the number of rectangles, then we're looking at the limit of this as n approaches infinity, right? What happens when we have an infinite number of rectangles, okay? In this particular image that we have here, not for the problem, but for this image, what is n? N here in this problem, or in this image, this graphic, n is equal to 4. So that would make sense that b minus a over n would be 1/4, right? That's the width of each one of these rectangles. Well, what about the height of each one of our rectangles? Well, the height of each rectangle here is going to be f of, so 1/4 I. And what is I here? Let me use a different color for that. What is I here? I refers to that just specific order. So in this case, for this first rectangle, I is equal to 1. I is equal to 2 for this second rectangle. I is equal to 3. I is equal to 4. Well, if that's the case, then f of a plus, so we're starting out at a, plus 1/4 I. 1/4 I. So the output at 1/4 would give us the height of that rectangle. The output at 1/2, and this is all just going back to the previous problem that we did, gives us the height of the second rectangle, and so on. This is just a way of determining the height of each given rectangle. So hopefully that makes a little bit more sense as to what's going on in this formula, but remember, we're just now doing the same thing that we've done, but we're now going to take the limit of the summation. So since we're taking the limit of the summation, we're going to go back and use those same summation formulas and properties we used in our previous lesson. So check back in the beginning part of 11.5, where we discussed the limits of summation. So I'm going to do a problem for you guys here, and then I'll let you guys try the second one, and you guys can check your solutions afterwards in the School Loop Locker. So let's go ahead and work through these. So same function, but we're just now going to answer the question of what's the exact area underneath this curve. So the area is equal to the limit as n approaches infinity of, in this case, this being n, this being I, is 1, f of 0 plus, because we started out at 0, 1 minus 0 over n, I, 1 minus 0 over n. And we already kind of just discussed all this, but I'm just writing this out in the same formula so you can see what, is equal to the limit as n approaches infinity. Let's go back to this. This is going to be a bit of writing, so I'm just going to give you a heads up, guys. All right, f of, if we just clean this up a little bit, we have I over n times 1 over n. All right, now in this next part here, I'm just going to zoom in so handwriting's a little less sloppy. the limit as n approaches infinity, I equals 1, and now figure out what each of these things are in the context of the problem. We have 2 times I over n squared plus 1 times 1 over n. Okay? Remember what this is. This is f of I over n. This is this. Okay, that's a terrible looking arrow. Okay? All right. So now the limit as n approaches infinity of 1 n. Now this, if I just use some algebra here, 2i squared over n. I got to multiply everything by 1 over n, so this would become n cubed plus 1 over n. And now we're getting to that point where we can start thinking about how to use some of the same summation formulas that we learned. So just like we did previously, I'm going to factor out that 1 over n. And that's going to give me 2 over n squared here, just for this first term. I squared plus now this. And from here, if you don't want to do it exactly the way I'm doing it, if you saw an easier and cleaner way, and you probably did, of setting this up so that you can use those formulas, then go for it. But I got what I was hoping for. I got an I squared, I got a 1, right? So now I can use those summation formulas. So the limit as n approaches infinity of 1 over n, bring down that 2 over n squared. So I got n times n plus 1, 2n plus 1. There's my first formula. And then plus, that one's easy, just 1n, or just n. And before I move further, let's clean this up a little bit. 2 goes into 6 3 times. And, oh, well, let's not go do too much at once. So now we got the limit as n approaches infinity of 1 over n. 2n, let's see here, 2n squared plus 3n plus 1 over 3n. All of that plus n. And let's continue this up here. Okay, so equals the limit as n approaches infinity of, now let's distribute that 1 over n. So 2n squared plus 3n plus 1 over 3n squared plus 1. So can't forget about that. And I promise we're almost done. So now let's divide everything by 3n squared. So that gives me 2 over 3 plus 1 over n plus 1 over 3n squared plus 1. And that then gives me 2/3 plus 0 plus 0 plus 1. And that just comes out to 5/3 units squared, or approximately 1.667 units squared. Okay, and there we have it. So it is a bit of work to use the summation formulas and to constantly use this formula. I get that. The good news is when you get to calculus and you get the hang of this and you understand how this is done, there are a number of different shortcuts you can use to actually get these values much, much faster. But right now we're just in the building block stage of our understanding of how all this works. Okay, so with that said, I'm going to let you guys try problem B on your own, but I will have the solutions posted for you.